Hi everyone, welcome to today's lecture of Introduction to Machine Learning and its application in data prediction. My name is Omar Ali and I'm a robotics engineer by profession, and I'm currently associated with German Research Institute for Artificial Intelligence as a machine learning scientist. Well, today's lecture is more about the introduction to machine learning, so I will try to explain the very basic concepts of machine learning in a very abstract way, not going into too much details of the technicalities. So, the synopsis of my today's talk is as follows. I will try to address the questions, the very basic questions of like, what is machine learning and why do we really need that? Afterwards, I will try to explain the workflow of the general machine learning techniques. Afterwards, I will try to explain the two main broad categories of machine learning, like supervised and unsupervised learning. Afterwards, I will try to explain a structure of the neural networks and how do they really work. Afterwards, I would like to throw some light on deep learning or deep neural networks. And in the end, I will try to explain the use case of data prediction and how machine learning can be used there. So, starting with the very basic question of what is machine learning? At the very first point is that machine learning is a subset of artificial intelligence. And it is a field of study that allows the computers the ability to learn without being explicitly programmed. They can learn from experience. Means, as said by Herbert Alexander Simon, that learning is any process by which a system can improve its performance from experience. And machine learning is concerned with the computer programs that automatically learns from their experience. So, in this world, right now we know that we have humans and we have computers. The basic difference between the humans and the computers is that the humans learn from the experience, and computers need to be programmed. They need to be told what they need to do. So the question is, can we make the computers learn the way humans learn, means by experience? And the answer is yes, we can do that. And that's what precisely the machine learning is. So now, for the computers, the past experience has a term that's called the data. So now let's take a small quiz. On the left column, you have the input, and on the right column, you have the output. Let's say the input is 3 and the output is 9, and then you have the input of 4 and the output is 16, and then you have the input of 8 and output of 64. So what will be the output for input 9? It's just quite a trivial solution for the humans. We know it's 81. Why? Because we know we learned it from the experience. Because the first element was 3 times 3 is 9, same as the rest of ones. So can we make the machines do the same thing? Yes. The answer is yes. That's what we are trying to do with machine learning. We are trying to make the computers learn the way humans learn. That's why the answer is yes. So now, since now we know that what machine learning is, now the second very trivial question is, why do we need machine learning? So I will try to give some arguments in the favor of machine learning, that why do we need it. So we need machine learning to develop the systems that can automatically adapt and customize themselves according to the needs of the users, such as the personalized search recommendations on Amazon or any other website. And we also need machine learning to discover new knowledge patterns from the large databases. For example, in the case of market-based analysis, market basket analysis, such as the drinks and the chips. And then we also need the machine learning to have the ability to mimic like the humans and to replace certain the monotonous tasks, such as the recognition of handwritten characters. And we also need machine learning to develop systems that are too difficult or expensive to construct manually, because they need some certain skills or they need some sort of a knowledge that is pertaining to some specific task. So to cope with all these things, we really need some intelligent system. And for that, we want to have machine learning in our daily lives. So now I will try to explain the workflow of general machine learning. Well, machine learning has three major parts, so to say, on a very broad level. So the first part would be the base knowledge, for which the answers are already known. And then we have the features, means we have the input. We get the features out of that input. The features could be any valuable information that could be used to make the output worthy of. So we have the features in the second step, and then in the third step we have the computational algorithm that actually processes that information that it gets from the features, and at the output it gives you the required output. Means if it is the supervised learning, it will give you sort of a prediction if in the case of classification, or some sort of a continuous value in case of regression. Well, in the case of unsupervised learning, the computational algorithm will give you some sort of like grouping, or the patterns that it extracts from the input data and give you in form of the clusters. The cluster is just like one of the techniques that could be used with the unsupervised learning. So this was just the general workflow of the machine learning. So now I will try to explain the main or the two broad categories of machine learning. Well, the two broad categories of machine learning are supervised learning and unsupervised learning. In supervised learning, we develop the predictive models based on the input and the output data. And in unsupervised learning, we try to group and interpret the data based only on the input data. So the two major tasks that could be done with the help of the supervised learning are classification and regression, while clustering is one of the things that can be done with unsupervised learning. Now coming directly towards the supervised learning. So this is the general architecture of supervised learning. Well, in supervised learning, it is a kind of a learning in which the system learns under some kind of a supervision. Means you have the input data and you also have the output data. So you provide this information to your system, and the system learns based on this kind of supervision. So it gives you the output at the end, and then output is compared with the labels, or you can say the targets. And then if the learning agrees with the labels, it says, okay, your system has learned pretty well. But if the target or the output of the system does not agree with your labels, then you adapt your system, you adapt the weights in your system, and it continues to improve itself such that the output of the algorithm agrees with the labels, you can say the target output. But there has to be some sort of a sweet point where you have to decide where to stop the learning so that it does not overfit. Overfitting means that it does not try to memorize the input data, so that it should be able to work as good as on the training data, as should be able to work well with the unknown data as well. So this was the training phase of the supervised learning. Well, in case of the testing phase, you have the input data, you just extract some features out of it, just like in the case of the training, and then you feed it to your pre-trained model, and your pre-trained model gives you the output. And this was the general architecture of the supervised learning. Now, like I said, the two main tasks that could be done with the help of a supervised learning, one of them is classification and other one is regression. Now, talking about classification. Classification is a task in which you want to categorize your input, like you want to put that input into some sort of categories. Either it could be, for example, in sort of the images, it could be you want to put your input image, for example, into the category of a cat or a dog or any other category. So the sort of a learning in which you want to categorize your inputs is called the classification task. And in case, for example, let's take the example in this slide where you have the input of images of dogs and the cats, and you have associated labels with them. So you feed these two to your network, and you want your network to be trained to differentiate between the images of the cats and the dogs. So at the end, it is just a classification problem because it is classifying the image into two categories. Okay, now coming towards the regression. In regression, you try to output a continuous output value. For example, it could be in the case of this example, this example describes the case in which you have like you want to predict the average salary, average income of a graduate based on the years of higher education. So it is a continuous output value that you are getting at the output of your system. So this is the kind of a system in which you want to have the continuous output values at the output. It's called the regression problem. Okay. Now coming towards the unsupervised learning. So in unsupervised learning, you don't have the labeled data itself, rather you have the raw data. You provide the raw data to your algorithm, and at the end it gives you some interpretation of your input data. For example, in the case of clustering, it will give you the clusters at the end. So this was the general overview of what unsupervised learning is. Okay. Now, like I mentioned before, different types of machine learning, and now I'll explain about like the different sort of algorithms that could be used with these sort of learning techniques. For example, in classification, in regression, we have like support vector machines, we have like discriminant like naive Bayes, and we have nearest neighbors, and then we have neural networks that could be used with these kind of like machine learning techniques. But in unsupervised learning, for example, to be specific with the clustering, we have k nearest neighbors, we have Gaussian mixture models, and so on. So these are the few algorithms that could be used with these two different categories of machine learning. So now I will try to explain a structure of the neural network, just to give the idea of how the neural network actually works. So in this image actually shows how the neural network actually looks like. So in this image we have the bubbles. These bubbles we call neurons, and in these neurons we put numbers, and we call those numbers as the outputs of those neurons. And we also put numbers on these arrows, and these numbers are called the weights. So and if you see the columns of the neurons, these columns of the neurons are called the layers. And in this case, we have three different layers. If you see, the left layer in red color is the input layer, the middle one in the blue is the hidden layer, and the one on the right in the green is the output layer. So to figure out what sort of a number, what sort of the output a neuron will have, a specific neuron, for example, take the topmost neuron in the hidden layer. To figure out the output of this particular neuron, what you do is you take all the outputs of the previous layer, you multiply them with the corresponding weights that go into that particular neuron, and then you add them all together, and that will give you the output of that particular neuron. So now you know that if we put numbers into the input neurons, how do we get the output at the output neurons? Because the procedure I explained for the one neuron is done for all the neurons in the hidden layer, and then for the output layer, and then we get the values at the output. And also to get the output values, since like I mentioned, we can have any value at the input, we can get any value at the hidden layer and get any value at the output. But for example, let's take the example that you want to classify the handwritten digits. For example, in the case of the MNIST. So in that case, you want your algorithm or you want your network to give you some sort of probabilities at the end of the network. So in that case, you will try to squash the values, these output values of the neurons with some sort of like functions that you call activation functions. Let's say the sigmoid activation function. So you could use these kind of activation functions in your neurons just to squash the range of those output values that you will get at the output. So like I said, we can take the example of classifying the MNIST dataset, means the handwritten digits in the MNIST dataset using the neural network. This is one of the samples. This is one example of the samples taken from the MNIST dataset. Here the image is like 28 by 28 pixels of different images of different digits. So in this case, what you do is you have like instead of just making a neuron with instead of just making a neural network with 3 input layers, or rather what you do is you try to make the neural network with 784 neurons. Why is that? Because in the case of these images, which are like 28 by 28, you just like flatten them, and like 28 by 28 would be equal to 784. So you flatten the image, and then those number of like vector, the size of the vector will be like 781, like 784 by 1. So that's why you need 784 input neurons at your input layer. And then since we are trying to categorize these images into 10 different digits, so we need to have 10 output neurons at the output layer. And how many neurons you can have at the hidden layer, it really depends on you. And it's just I mean, there is no hard and fast rule of defining how many neurons that you actually need at the hidden layer. So many people will choose the number of hidden neurons to be as equal, at least to be as equal to the input neurons. But it can be more, and you can also have multiple hidden layers. So in that case, you just make your network a deep neural network, and then you can say that your network is doing the deep learning. Okay. So, okay. Now, let's say in the case of this MNIST digit that you provided at the input, your algorithm provides something like this at the output. So it means that your algorithm thinks that it gives you, like we said, we want to have the output as a probability. So just consider this to be a sort of a probability that it is giving you at the output. So where each neuron represents that how much the algorithm thinks that the input number is which number. For example, if you give a digit 1 at the input, so the output neuron 1 is corresponding to how much the algorithm thinks the input number is 0. And in case of the second neuron in the output layer, that neuron will determine how much the algorithm thinks the input digit is number 1, and so on for all the 10 neurons. So in the case of this output, if you get, let's say you get this output that you can see in the slide on the right, it says that the algorithm thinks that with the probability of 0.9 that the input number or the input digit that you provide as in form of the image is number 2. So this is normally what you get at the output in this case. So, but now we know that how you feed forward all the things through the neural network. But in this case, since this is the output, but what do you want your network to do? So you want your network to produce the outputs as close to your labels. So in that case, you also associate the labels with your input images that you provide to the network. Let's take an example of the label that I just said, that's just shown on the right side of this slide. Now here it is, like it shows the number 3. So if your network provides some output at the end, so you just have to make sure your network tries to adapt its weights in such a way that the output is as equal to the one you are providing in sort of a label. So, but how it adapts its weights is through like the gradient descent and through backpropagation channel. That's something that I'm not going to touch into the detail right now. That's beyond the scope of this lecture because it is just merely the introduction, so I'm not going to touch that. So this was just the general idea of how you feed forward your network, feed forward the data into your network and how it gives you the output at the end. So now, just like I mentioned, that if you increase the number of layers in your network, it becomes a deep neural network, and that's the notion of a deep learning. So from this image, we can see that where the deep learning actually resides. In the broad spectrum of artificial intelligence, machine learning is a subset of artificial intelligence, and in the subset of machine learning, deep learning is also a subset of machine learning. It is just a part of a machine learning. So the basic difference between the traditional machine learning and the deep learning is that in traditional machine learning, the feature extraction part is normally done manually. You use the handcrafted features. In the case of the general machine learning, it means you have some user or you have some like computer programmer who is sitting right there. He's taking the input in form of the images or whatever. He's trying to extract some features, and then using those features, it provides it to the network. But in case of the deep learning, this part is merged inside the network itself. So that's the general notion, or that's the general difference between the traditional machine learning and the deep learning. So now I will directly go towards the introduction to the use case that we were talking about earlier, the use case of chatter prediction. So in industry, we know that robots are being used for many different machining operations, such as milling operation or like trimming operation or like whatever operation. I mean, they are being used in a lot of different sort of operations. They are being used. So let's take the example of the milling. So we know that the robots have some certain kinematics, and then they are also holding the end effector, and they are also holding some sort of a tool at the end through which they are trying to operate on some sort of a workpiece. So what we need in this case is we want to avoid the robot to make some sort of vibrations that at the end will make the object deteriorate, or that will make the object lose its final quality. It will not only damage the product itself, but will also damage the tool of the robot that it is holding to perform that operation. So in this case, what we need is we want to perform a machine learning task. We want to learn a system that tells us beforehand that, okay, this specific configuration of a robot and this specific configuration of the machine tool will not produce those vibrations that we call chatter. Because if those vibrations are produced in the milling operation or in any machining process, you can see the end quality of that product will be damaged. So here is just an example of a robot trying to perform some operation on a workpiece. Here you can see that we have a robot. Like I said, the final quality of the robot, like in case of chatter being produced or not, really depends on different sort of parameters, such as the kinematics of the robot, means its XYZ coordinates, or it's both at the end. And then it also depends on what sort of like tool you are using. For example, what is the number of teeth of that tool that you are using at the end, and what is the diameter of that tool, and how much do you exert the force when you touch the object, and at what angle do you touch that object, or that tool with your object. And it also depends on how much the speed of the spindle that you are using to perform that operation. So all of these things really determine whether that certain configuration of the robot and machining tool will produce a chatter or not. So we want to develop a system that will predict beforehand if a certain configuration is good enough for performing that operation is not. So in this case, we had used different approaches to solve the problem. For example, we used classification, because it is just merely a classification problem where you have to decide whether this configuration will produce a chatter or not. So it's just a binary classification problem. So we started with the simple support vector machine, and then we also used the neural networks. So in this case, the input to our neural network, just like I try to explain the structure of the neural network, I'll try to stick to that, and I'll explain the input feature that we used in this case for our neural network was that we used the parameter of number of teeth of the tool, we used the diameter of the tool, we also used the angle at which you insert the tool to that workpiece, we also used the width or the cut of that radial engagement with that object, and we also used like the spindle speed at which you are trying to rotate the spindle. We also used the depth of cut, at how deep you cut that object, and then we also used different kinematics of the robot as the input features to our neural network. And as the output of the neural network, what we got was the prediction about either this specific configuration will produce chatter or not, and how confident our neural network is how confident it is about that output that it is giving me. Either you can say if the neural network gives the output that it will not produce any chatter, but how confident that is means it says, let's say neural network says that I'm just 20% confident about this configuration will produce chatter or not. So we are using this information at the output to make it better for to make it better for the whole operation to perform fine. Okay. So in this case, the data collection was done through simulation. Rather, we had two options, like either we could use the real robot to collect the data, but in case of the real robot, it was like sort of an expensive procedure, because in that case we would have to use the real robot and the real objects on which we could use the milling operation and all those, and then observe that which configurations produce the chatter or not. So it was highly time consuming and costly process. So we did not, and secondly, we did not have any access to the real robot, so we had to rely to the second way of getting the data, that was through the help of simulation. So we used the simulation graphs that showed a response between if we change the spindle speed and the depth of the cut, how will the pattern produce the chatter or not. So we use those graphs that are called the stability lobes diagram. We use those graphs, we use those simulation diagrams to get the data, to collect the data. So in reality, for each robot configuration, we had 160 different machine tool configurations. So for the proof of the concept, we just used two specific robot configurations. So in total, there were like 320 different machine tool configurations that we used to acquire the data. So then there was also a data sampling technique that we mentioned, that we divided the whole data into 6 equally spaced bins. For example, in our case, from 0 to 2000, 2000 to 4000, 4000 to 6000, 6000 to 8000, 8000 to 10,000, and 10,000 to 12,000. So we equally divided the bins into, we equally divided the data into 6 equally spaced bins. And then we sampled the data from each bin in the equal amount. And the data sampled from each bin was equal to the minimum number of points available in all the bins. So this is how we did the sampling, and this was kind of more like an intelligent way of sampling rather than taking any data points for training. So this was more like the intelligent way of sampling it, and it had a huge effect on the performance or on the betterment of the performance of the classification accuracy. So now the procedure that we adopted in this case was that we trained the model on data points of one robot configuration, and then we fine-tuned the trained model on the data points of the other robot configuration. Then we stored both the models and their robot kinematics information in a memory module that we call lifelong memory module, because it was like trying to store the information as the process goes on. So in the case of so now, like I mentioned, we train on one data configuration and we fine-tune on the other. We stored the model and their robot kinematics in the memory module. Then in the case of any new configuration, we use the pre-trained model for fine-tuning that has the smallest Euclidean distance between its robotic kinematics configuration and the robot kinematics configuration of the new data set that we are getting. So if the Euclidean distance of the nearest neighbor is below a certain threshold, then we didn't need to store that model into a memory module. Rather, in that case, we could directly use the model for prediction on the new data set. This was the general procedure that we opted for in case of training the network and storing the models in the memory module. So this diagram actually shows the result that we got at the end. So on the x-axis in this diagram, you can see that in the x-axis you have number of points of new configuration used during the fine-tuning. And on the y-axis, you have the test accuracy of the fine-tuned model on the test points of the new configuration. So it shows that means you need as minimum as 100 points to reach to the accuracy of 90%. And if you have like around 300 to 500 points of the new data points of the new configuration, then you can reach to the accuracy of 95%. So certainly this technique had shown in simulation that this is a valid approach in at least reaching to the accuracy of 95% when it comes to the prediction of the chatter. And this is the deployment diagram of this whole system that I explained, that in this case the data collection node is responsible for collecting the training and the test data, and it is also responsible for storing the training data into the database. And then you have the machine learning node that is responsible for getting the training data from the database and training the data either for the pure training or for fine-tuning. And then it is also responsible for storing the trained model into the model database. And then you have the prediction node that is responsible for interacting with the data collection node to get the test data. And then it also gets the specific trained model from the database, and then it performs prediction and it returns the result to the client server. This is the deployment diagram that how it should be done, how data should be collected and how data should be transformed back to the customer. So now as a conclusion, like I said, we just need approximately 100 intelligently sampled points of the new configuration to fine-tune to get the accuracy of around 90%. And if we go like around 300 points, we can reach to the accuracy of like 95% on the test set of new configuration. And we also conclude that the number of points that we use for pre-training the original model, if you increase that number of points, you require less number of points during the fine-tuning process to reach the accuracy level of 90 to 95%. So I would like to conclude my presentation with this conclusion, and yeah, thank you so much.